Everyone, my name is Jose Hernandez. I'll be your presenter today. I'm one of the research specialists at the Research Computing Center, which is the main, we administer the main supercomputer on campus, right? And we help researchers with their research questions and how to use not only R and Python and MATLAB and all the digital tools that you need to do your work, okay? So today we'll be talking about Introduction to Parallel R. For those of you in the room who has used R before, okay. So today we'll be doing an introduction on how to use R in parallel, right? How to do parallel computing with R. So we won't only cover the R basics, right? And hold on with me there, but we'll also cover particularly what is parallel computing and what can it do for our research, okay? So for those of you in the room, you should have been able to log in to Open On Demand, which is the main way for us to access the supercomputer on campus and how we'll be using RStudio there. Now, we already put in some files there and I'll guide you through how to use them there. Everybody on that page with me, with the login? Well, if not, we have the rest of the team in the back. I have Alex Townsend and Lee, another one of our research specialists, and also Casey McLaughlin. If you need anything from us, just let us know, okay? And they'll be there to help you as we go along. All good? Okay, so first things first. The to-do list for today. First, we're going to go into what is parallel computing, right? What do we mean when we say this? What does it mean to do parallel computing? Then we're going to go into an RStudio overview, right? For those of you familiar with R, this will be redundant, but we'll still talk about what is RStudio, how do we use it? Then we'll talk about the library Parallel, right? So, for those of you familiar with Python, for example, a library in R similar is a package, right? It's a group of code that we can reuse, with particular functions that we can use to make parallel computing easier. And lastly, we'll do a little intro if we do have time. I think we will to send us some mid script for large parallel computing job. Okay, large with the air quotes. Okay, so let's get started. So parallel computing can be thought of like, imagine you have a class project, right? And you're the teacher and you have to design and separate that project along your students. So let's say you're creating, right, a poster and you're creating a PowerPoint presentation and you're creating an actual hands-on model. You put each group to do a part of it. And at the end, they bring all the parts together and you get a result. Right? So it's the same thing, but in this case, instead of sending the task among students, you send them among the computers. Right? So you make each core or each processing unit do a thing. Right? And that's when we get into some nomenclature. That's important. So when we say cores, we mean the individual CPU core. So you can think of your laptop. Your laptop has multiple cores in it, right? That's why it can do multiple things at once, right? Have this open, that program running, right? It has multiple cores on there. For ease of explanation, we call our individual computers in a big supercomputer, we call them a node, right? And that node has multiple cores inside of it, right? So those are the two separate things on there. So you can think of the node as the computer and the cores as the processing units inside that said computer. So when we do parallel computing, it's actually, we talk about two things. One is what we call distributed computing. Actually, let me hide this so you can see the bigger picture. Right? Once we call shared memory, the one on your right-hand side, right, where we have each processor and they all access the same memory. What do we mean by that? Let's say you're running a program with some code, right? They all have access to the same program and code or data that you're running, right? Now, if I'm running something really intensive, I will try to coordinate between different cores. And that's what between different processors, right? And that's what we talk about, the one on your left-hand side, which is the distributed computing example. In that example, each processor has an attached memory and I need to send messages between them. Okay, so good example for this one is, imagine you're in a kitchen, right? And somebody's making a sauce on one side and a pasta on the other, and I have the salt. Somebody else needs the salt. I need to pass it, right? That's a message passing between the both. And both of us are doing different things, but we need a thing in common, right? And that is that memory, right? Does that make sense? Kind of? Okay, so these are the two big paradigms of parallel computing of the things we'll do today. The first one we're going to do is a shared memory one, right? And that's the one you'll actually be typing and coding. And we'll see a distributed example, which get more complicated, right? You can see that the message passing will present a significant challenge when code gets bigger. So we'll run an example of that, but you won't actually type it. Okay, does that make sense for today? Good. Also, if you have questions, a pretty small group, so go ahead, raise your hand, stop me. I know I can sometimes get carried away, so let me know. Okay, so that we're down. And so R makes this super, I was gonna say super easy, but it makes it easier, right? Than other programming languages because R builds in a parallel package that gives you very high level functions that you can use to do parallel computations. In other programming languages, you may have to do more legwork to set up parallel programming, but R gives you some built-in functions that actually come with the base installation of R and RStudio. If you have it in your laptop, you actually already have it installed, right? The lessons you'll learn here today, you can use them for your laptop to take advantage of laptops today, which have 4, 8, or 16 cores that are really high, okay? So this will translate to what you have. Having said that, I'm now gonna move to the interactive part of the presentation. Okay, so I'm gonna escape out of here. And for those following online, if you do have an open on-demand account with us, you can go ahead and log in. You will not have access to the workshop accounts and the files, but you can type it up with me. Most of them are not, except the last few exercises are not reliant on any data or additional data. Okay, so if everybody here on this page for me on open on-demand, good. Okay, so you're gonna click on interactive apps, right? And we're gonna be using the RStudio 2023 one that's there. Okay, so once you click on this, it'll open up the. And this is the main way we use the graphical user interface for the supercomputer. So when you submit a job, right? Let's say here we're gonna run RStudio, we're running it on the supercomputer. You're not running it on that computer that you have in front. Okay, so a couple things that are gonna be default, right? We're gonna tell it how much time do I want to run this program for. Leave it as a default 3 hours. It should, right, the default there should be 3 hours for all of you. If it's something else, you can change it to 2 or 3, should be fine. And the important part here is that change that number of cores from 1 to 8, right? We want to try to do some parallel processing here and have more than 1 core, right? And you should have 16 Gs of memory. If not, any number above 8 is good enough, okay? So it's good practice to keep 1-to-1 cores to Gs of memory, okay? Unless you're dealing with some pretty big stuff. Other stuff that we can change for your own edification. If you want to change the R version, you can on your own. Keep it where it is. Don't play with it. It's just for if you have any legacy R code, just know that that's an option, right? We know that many times old research projects float around departments, so you may need to keep legacy code running. Okay. Once you have that, you can click launch, right? And this will submit the RStudio job for the open on-demand. We have to wait. This is queued across campus. Remember, the HPC is a shared resource on campus. And then this will queue up our jobs, and then we'll get access to running RStudio on the supercomputer. Other things that you should, while it queues up, and there you don't have to follow me on this, just so you know. Other cool things that you have on here are the file directory, right? And that will show you what files do you have on there. And for your own works and purposes, you can actually upload and download files from it, right? So if you do have an RCC account in the future, or you have it now, you can upload and download files there to your file directory and also see what's in there. Right now, you should only have about 5 files in there. This is your workshop account. It's only the files that we're going to be using today. Right? You shouldn't have, there's nothing else on there. Pretty much an empty account. Okay, so let's go back to my interactive session, see if it's running. It is, right? You'll notice it's running because it's running and it's green. Okay, so when that's done, you click on launch RStudio. And it should give you the regular RStudio window. Is it okay, or do you want me to zoom? I'm gonna zoom. All right, that's better. Let me know if yours did launch by raising hands quickly, just so I know. If it's still queued, it's fine. Let me just take a minute. Okay, while some of them come up, I'm gonna give you an overview of RStudio for those who have not seen it before. So RStudio has on your right-hand side, it keeps the environment. So those will list the variables that we use while we're programming, right? The bottom pane on that right-hand side is gonna be your file directory that you're currently on, right? And you can change what that working directory is, right? But for now, we're gonna keep it as it is. This is our big home directory. But if you ever have a ton of files for different programs, it's good practice to move into the directory you need to be in. Then we have the console on this left-hand side. And when you open a file, you're gonna see it on top of that console, okay? So everybody good on RStudio? You have it on? Okay, oh, pretty good. So now we're gonna click on the one called Parallel R Workshop Student Version, the one that ends in RMD, that means R Markdown. Wow. Okay. And it should open it up for you. See that? It'll open up. It will open up on the top left hand side. Okay. Now you will see that most of it is empty because we'll write it up. Okay, we're gonna be writing up the code. Right now, anybody has used notebooks before, our Markdown notebooks? It allows us to combine some text, so you'll see text up top, and anything that's between the dash, the top commas, that's code blocks that we can run, okay? So you see that each one of these has a play button on the right-hand side, and it will let you know that you're running. Okay. That's pretty much the intro to RStudio. Now we'll actually, yes, question.
Yeah, will this workshop include writing an R script for parallel computing and job submission?
Yes, at the end of the workshop. Good. Okay. Any other questions? We'll start writing. Okay, so I'll be actually live coding with you. There will be mistakes. We'll be backtracking. That's fine. That's part of the idea. Okay, if you see any mistakes on the board, yeah. Okay. As the way we like to do these things. So the first thing we're gonna do is actually load the library parallel that we're gonna use. To load a library in R, we type library and then parentheses. And you'll see that I'll give you a ton of suggestions on there, right? To tell us what library do you wanna use, and we're gonna install the parallel library. Right, it should give you the nice help box that says support for parallel computation, including random number generation, and click enter on there. And that's, once you write that line, you can click on deploy and you should see it run. All good. Right, that means that the library parallel is installed and we can use it. Okay. Cool. From there, I'm just gonna, each one of the blocks means a code, not a code line. We'll be doing longer blocks, but that way you can follow around. So now that we've done that one, we're actually gonna bring in a data set that comes pre-built with R. R gives you some data sets to experiment around with, and we're gonna use one of those today. So we actually call this one with the data and parentheses. And here you see all the data sets that R gives you. Right? R gives you to try on stuff. A bunch of them are big or bigger. I'm gonna use the Iris data set, pretty classic. Let's use a pretty classic data set on our workshops. So click on the Iris one. Important for this one, it's not enough to just type it, you need the air quotes in there. That's why I clicked on it, it autofills the air quotes. I'm a little bit lazy coding, I like clicking whenever. But if not, just type data, air quotes, Iris, right? And once you load it, you should see something appear on that right-hand side, right? Your right-hand side should now show that you've loaded that data set called Iris. And actually, if we do click on Iris, it'll show us what the data set looks like, right? Data set has 150 records. Each record has 5 variables. They're all plant irises, right? And it says sepal length, sepal width, petal width, and the species of that specific plant. And it's not topical to almost anything we do, but it's nice to have a really small data set to try stuff. Everybody was able to load their data? All good? Okay. Any questions online? So I haven't done anything parallel yet. Oh, but we'll get there. Okay, so going back. So now we have the data, and I want to see a summary of it. What is a summary? Means just summary statistics of it. So for that, I type in the summary command, and I call in the data. In this case, I can just type iris itself, and you can see that it specifies this is the variable that I can access because it's already been loaded into the environment. And go ahead and run it, and you'll see some output here. And for now, for our workshop, this is not important, but it's a nice intro to seeing what a data set is. It gives you the quartiles for all of them, min, max for all of them, right? So nice, a nice overview of what's in, right? But it doesn't really tell us anything right now that we can use. Okay. So now we're actually gonna write up a regression. Right, so anybody that's have dealt with regressions before? Yeah, in class? So it allows us to create a model, right? To try to predict a variable based on other independent variables that you have. Okay, that's a pretty wordy expression, but let's write it up. So in this case, we defined the model. And instead of using an equal sign, if you're accustomed to Python, you'll be very familiar with the equal sign, but here is the caret with the dashed line, it's an arrow, okay? So model arrow, and that tells us this is defining a variable, and we'll call LM, right? And then you'll see that it gives you a helper for that, like what the LM should have, and we're gonna use sepal dot length. Right. And we use the little squiggly bracket, right? To call the other variable that we're gonna use as the explainer variable, comma, data equals iris. Now, why am I specifying at the end what the data is? Because right now I'm telling it, so create a model between sepal length and sepal width, but they don't know where that is. So I need to specify where the data is coming from. In this case, iris. If you are working with multiple data sets, it's important to keep track of which one's which. Right? And I'm gonna create also output a summary of said model. Okay. Let's scroll down. Actually, I'm gonna take this console out. And that. So once you run it, right, you should see it will call the linear model there and it'll output the, so this is a traditional linear model, right? Like y equals mx b, right? It will give you the intercept, the slope for that linear model, trying to predict sepal length correlate based on sepal width. Okay, so that's where that's coming from. It'll give you the f scores, the p values on it, and to give you significant. This is all very statistic stuff. For now, the important stuff is that this is a function that's being applied to the data, right? And we will grab that function and repeat it many times. And that's going to be the parallel part of our seminar, okay? So we're going to be using this linear model and actually run 28 of them at the same time. And that's the cool part about it, instead of running 28 one at a time, okay? So that's what we'll be doing there. And the important part about this is time. How much time can I save by doing stuff in parallel, or my messing time, right? Because that's the other thing. Parallel has some quirky things and quirky costs, and we'll see some of them here. So this block actually is already written, the next one. And to observe parallelization, we need to observe time. So now we're grab that model line that you just created, the one that says model, the one that defines the model itself. And you can actually paste it into the single regression time. Okay. And when you play this one, it'll actually tell you how much time did that take. And it should be super small, 001, 002, 004, right? And that's in seconds, so it should be nothing, almost instant, because it's a really small linear model, really small data set, you'll be fine, okay? But it gives us an idea. First of all, I want you to notice that there's two times there, user and system, right? System is coordinating the system behind the scenes, memory, communication, anything that is not counted in the user will be in system, okay? And then elapsed is the total between the two. Now, there will be some hidden runtimes, called like start and end of the runtime, and we'll see how those look up in the parallel. Okay, so for a single calculation, super small. Now, this next code block, I'm actually gonna ask you to read it and run it, but we're not gonna write it. This is just creating a list of every possible linear model between all four of our variables. Right, so let me run it and then I'll explain doing that. So once you run it, you see that you create a data called model. You can actually go grab it. A data called all models list. So I'm actually gonna move and rotate. So you can see here, same on that side, that you have a list of all models and each model has a model formula. So this one is trying to predict sepal length on sepal width, sepal length on petal length, sepal length on petal width, and then it tries again with two, picking two for each one, picking three for each one, right? And the total is 28 models in total. Now, why are we doing this? Sometimes we have a variable, right? And we're trying to find the best combination of predictors for it. This allows us to run all those combinations, right? Instead of trying out and seeing which one I add and which one I take out, I can just run them all at once. Now, this function is not standard. I wrote it myself, but it was just to be able to produce a quick list of all the models, in this case, 28 of them, but this is a pretty small data set. If you have, that says census data, and you have 10, 15 columns, and you're using all those variables to explain, the models are gonna get pretty big if you wanna try every single one out, okay? So that's where we're going. Now, the next thing we're gonna do after running that one, it's actually creating a function. Why do we need a function, right? Because we're running the code in parallel, correct? We're gonna run that linear model, but we need to be able to run them all at the same time, which means I need a reproducible code to apply it every time. And this is where we're gonna write it here. Okay, so the function, to define a function in R, I'm gonna go run. I'm gonna call this one run regression. That's gonna be my function call. Right, and the same thing with the arrow and with the caret and the line. And to define a function, you can just call it function formula, right? Okay. And then we open up a caret. Okay, so you should have this now, right? This function called run regression, I said it's a function, and in there I'm gonna write it. Right now it does nothing, right? And we want our function to not only do a model, we want it to return the summary, right? Every function returns something, returns some result. So let's write it up. In this case, we do model. Say again the model, and we're gonna define your model with a formula, comma. And we're gonna make sure that it's data equal iris, right? And this is gonna call the formula in from our list of models. It's gonna be like, oh, let me grab that one, try it out. Next one, try it out. Next one, try it out, okay? And then we are gonna return summary of that said model. Okay? It's important that you just don't write summary model. It's important that you write a return statement so that that function actually outputs something, okay? Now, if you do get an error here, it may be a parentheses, it may be a bracket that stays open, right? R is really good at producing both of them at the same time, but if you do get an error like that, just let us know. It could just be one of those syntax errors that drives us crazy, all right? So let me go ahead and good. Yeah. So once you run it, you should see a function right here on your right hand side. It says run regression function. Good, we made a function and it's there. We still haven't used it, right? And for that, we actually need to write it. Good. Okay, so for this next one, right, I'm gonna run it linearly. I'm gonna run all 28 of them one after the other, right? So, and we're gonna see how much time that takes. So let's write it down. First, we're gonna define the time one. I call it time linear apply. You can call it whatever you want. You can call it time, right? Just making sure that we keep the names pretty standard. Now, clarification here for the time, to the system time calculation. It's a parentheses and then a bracket, okay? It'll autocomplete both, but just so you know that that's what it's asking for. So and now we are gonna linear apply. Now, that's the function that's gonna say, apply this function to all the things in that data set, right? So linear apply, that's what the L stands for, right? And later we'll use the parallel apply, okay? So linear apply, and then we call first the data, in our case, all models list, and it should autocomplete it for you. Or whatever, yeah, it should autocomplete that one, and then we're gonna call the function. Remember to call whatever name you actually put to the function there, okay? And then at the end, you don't have to do this, but I'm gonna print the time to L apply, right? So we can see how much time it's taking us to run all 28 models in sequence. Okay. Give you a moment there to see it. Also, for those online, we will, and for those here too, we will send out solutions for this, right? Because we know you won't be able to download them at the end, but we'll give you solutions through email for those who sign up. Okay, whenever run it there, now I'll discuss why, maybe finish it up. You see now it's not taking even a second, but now it takes 0.04. Before it was taking 0.001, 0.002, right now we're at 28 models. And we're already taking 0.04, which is not a lot, right? Good timing, but now we can imagine what would happen if it's millions of rows, right? Or it's a ton of columns, and we want to create models for all of those, right? And the reason I'm doing this imagination exercise is because it will take us a long time to actually do a real data set in here, right? And typing it up. So you can see that the time increased, okay, on the user side, but the system one stayed the same. Okay, I want to be very clear about the distinction between them. Okay. Now, till now, we've done everything linearly, everything sequentially. Now we're gonna shift gears and go to the parallel side, right? So what happens if I want to run all 28 of them at the same time, or kind of at the same time, faster? So I want to, for example, in our case, if I have 2 cores, right, I want to grab these 14, you do them, and these 14, you do them. The time should go down, right? Because I have more people working on the same issue. Okay, so before we do that, I'm gonna make you run the next one. It's completely written for you. And it should actually output 2 numbers, and they're kind of important. So they'll be different for all of you, depending on which machine your job landed on. But it's important to know that R will let you, if you use the detect cores function, it will detect all the cores in that computer. Okay, important part, in that computer. So if you are running on a node on our supercomputer on campus, that node may have 24, 96, right, nodes. But that doesn't mean all of them are available for you to use. Why? Because our job only asks for it. And this is a like a high performance like issue, right? Because you requested it on our system. This will not happen on your laptop. All your cores are available to you, right? But just as a caveat there, as you can see, if I search for how many CPUs did I get, right? The system give me, they gave you 8. That's how many you have, right? That should be the second printed number. So that means that we can only parallelize across 8 cores, not 24, not 96, or however many cores your particular node ends up having. Right? Anybody had a different number than 24 when you run that block? How much?
16.
16?
Yeah.
28?
28.
28, yeah. So we have different amount of nodes, different amount of cores in each node, okay, on our computers. Okay, so also you'll see that I wrote 96 is because the one I was on had 96 at the time, but it's not. So this last selection is actually where we're gonna actually run the parallel one. So same format as the top one, so you can actually copy this one, the times one that you did, the L apply one. Gonna use it again, but this time, instead of L apply, I'm gonna call it MCL apply, which is the parallel function for applying a function over and over again. Right? Change all the ones that said L apply to MCL apply, and same thing with that function. So we're gonna use MCL apply all models list, and important, there's a third parameter. Parameters is what we call the things between the parentheses that we're treating the MCL apply function. That one's gonna be the number of cores I want to use. In my case, MC.cores equals 2. not 21, definitely not 21, but 2, okay? So that tells me run this apply function using the all models list, using the run regression function, but split the jobs across 2 cores. Okay? I can increase it, I can do 8, I can do 16, however many I have available, but we all ran 8, right? So I can only go as high as 8, right? For now. So let's do it with 2, see how it goes, and make sure that you also change the one that says print, so that it prints out the MCL apply time and not the L apply time, right? So you can see if there wasn't a speed up and what that speed up was, okay? Go ahead and run it. So, yeah. So we did get speed up on the user side. Our original time was 0.04. Now we're down to 0.028. But on the whole, it was 0.006 slower. Why was it slower? Because now we're getting system time. Right? System time comes from managing the 2 cores, right? Managing the memory, right? And having to actually make them work in concert. Now, this is it has a name in computer science, but the idea is that not everything should be parallel, right? Because not everything will get a speed up. Now, the more cores I add, the more system time I will incur because I'm trying to manage more resources, right? And then you can see that the user one is pretty much split in half from what we had before because we're running half and half on both. Okay. So in this case, what would I need for this to be an actual speed up? I would need a bigger data. I would need more models to be run. And that way the time that I would save in the user wouldn't pass, right? Because the system time would remain close to that 0.2, 0.3 time, right? Coordinating just 2 cores. Does that make sense there? Why the time user 1 went down, but the system 1 went up? If it didn't, just ask him. Okay. This is just a nice lesson about parallelization. You have to be careful what we parallelize, right? Because not everything is an improvement. Now, this is a super small data set, 150 rows. You probably have a class that has a bigger data set. They're grades. Okay, so I'm just letting you know that this is super, super small in the grand scheme. But does this make sense, right? And now, was this shared memory or distributed computing? The examples we talked at the beginning, was this a shared memory example or was it distributed? Shared, right? Because it's all here, right? They both have access, both cores had access to the environment variables. I didn't have to send out any memory, I didn't have to manage any messages. So this is shared memory, right? As long as you keep it below the amount of cores in a node, in this case, for some of you it's 16, some of you it's 24, as long as all the cores are in the same node, I don't need to do distributed computing. Okay, tricks? Perfect. So now I think that was the end of. Yes, that was the end of the RStudio one, right? And don't close the RStudio because we use it for the next one, right? But I'm actually gonna go back to the sheet. So the next one we're gonna do is what's called a multi-node, right? Using 2 nodes that have separate memory spaces. We want to run a job. Okay, so for that, we need to submit what we call a batch script, and which allocates resources on our supercomputer. Now, if you remember when we ran the RStudio at the beginning, you had to select time, how many cores, how much memory, right? We can do that in a programmatic way, not just in the GUI kind of way to write it up. And the way we do this is by using batch scripts. So this is how a batch script looks like, okay? A batch script has set some arguments at the top, which are the parameters of our job, or the thing we're running, right? And at the bottom, we have the actual commands that are being run. Okay? Have you never seen a batch script before? That's okay, right? Most people have not dealt with one before, so I'll talk you through what's on it. So the top one is just the job name, right? And when we mean job, we mean the program we're running with the data, right? That whole thing is called a job. We also have the next command, which is the -A command, is the Slurm account. Now, what are Slurm accounts? Think of them like grocery store lines. It says my job should go through this line. My job is express. My job is high priority. My job is from the engineering department, right? Because they have their own line because of the amount of cores they use. Generally, all students have access to the general access queue, which is called the GenAct queue. And you have access to backfill 1, backfill 2. We call it backfill because when we have a backup with general access, you can use backfill 1 and backfill 2. Okay. You also have access to quick tests for small programs that last less than 10 minutes. Okay, so those are all the Slurm accounts that you have access to. For now, general access works pretty well for most of what you're gonna do. You also can select the time. You can select up to 14 days on some of these queues for really, really long jobs. For any job, you can select, yeah, less than 14 days, and the format is days dash hours, minutes, seconds. Okay? You cannot pass 14 days on most of our queues. Okay? These two are the important ones that we're gonna discuss today, which is the big N and the small n, right? The small n is the amount of cores that I want. So that's what we used to define earlier. I wanted 8 cores, right? So that's small n. The big one is the amount of nodes. So think of right, remember the analogy? Nodes are the computer, cores are the processing units inside it. So in this case, I'm saying I want 2 computers, and on each one of those 2 computers, I want 2 nodes. Okay, is that right? Traditionally, we would not do this, right? I'll be like, I want 40 cores and I want 2 nodes because I need 20 and 20, right? Because I can get 2 cores in a single computer and I don't have to deal with memory. But for a very small example, this makes sense. If your program does not support distributed computing, you keep that big N at 1, right? There's no reason to change it. If you don't have to deal with memory issues, balance. Okay, keep it straight. Okay, keep it simple. So last part is the actual commands. Here I'm loading the module load R, which tells me I am using R. Keep it ready. I want this version, and then we're gonna submit our file. Right, we're gonna be like run this R file, which is the file we just had earlier, but this time I'm just running it all at the same time without having to press each section. It's just running all at the same time. Does that track how the bash script looks? It's okay if it doesn't. It's okay if some of them you're like, I still don't get the difference between node and core, but I will in 2 to 3 years time. That is fine. I've been working at this job for a few years, and I think I just got it today. Okay, so don't worry about it. Okay, any questions online before I take off the battery? No. Okay. So you've been a great class. This has been really good. I know it's small and not that many mistakes. Okay, so this is the summary, right? My job is called my job. There's a general access queue. It's gonna run for 1 hour or at most 1 hour. It's gonna use 4 cores in 2 nodes. It's gonna load R and run my script. Okay, so that's the condensed version of what my job is doing. So let's actually, yes, question.
Just a random terminology question. When you say Slurm account and queue, are those the same thing?
Yes.
Sure.
Yes. Alex knows way more than me, so when he quizzes me, I get started. But yeah, it's the same thing. Okay, so going back to the actual thing. Okay, so I did say that we're running a file, right? So what file are we running? For that one, we're gonna run the one that's called multinode-r.r, right? And when you click it, it should open it up. And you actually don't have to run any of this. Don't try to run it, it'll throw up an error, just read it with me. So the top ones are the same thing we had before, library parallel, data iris, we all this to create all the models, and we're creating our same regression. Up to there, it's exactly the same we did writing it up, right? Up to there. Now, once we get past the regression function, that's why I created this little header there. This is parallelization process. This is the part that's different. And the reason I wrote it up is because it's significantly different. Okay. So we are getting the node list from Slurm, which means what computer am I running? What's the number of that computer? And I'm getting the number of tasks. So how many cores did I get? I got 4. Okay. So that's what that calls there. And then we're creating this function is just a helper function, right? And then we're defining how many workers I want. Okay. So workers, you can think of the analogy we used earlier with our assignment, right? It's how many groups I actually have. Okay. So here's the cool thing. We defined 4 cores and 2 nodes. But as well, I can define 16 cores and then say these 4 do something, these 4 do something, these 4 do something, and these 4 do something, right? In this case, I'm saying each core will do a separate thing, right? So there's 4 of them. But I can say these 4 will do something together. Okay, so that's what the difference is with you workers, right? I can define a group, one worker can have 8 nodes. Right, so that's the difference there. Okay, then this is how R defines a cluster. And by cluster, it just means arranging those workers, right? So this, it calls it CL. And it makes the cluster. And then this is the part that makes it distributed computing, is that I make sure that I cluster export. Okay. Cluster export means to each of my nodes, send the variables, iris, all models list, and run regression. So both of my memories get the things, okay? If I don't cluster export, one of them is empty. One of them's like, I don't know what you want me to do. There's some code there, but there's no data to run on, right? You didn't send me anything. I'm empty. All right, so that's this cluster export right here. That's what that's gonna do, okay? So that's the most, if you take anything away from today, send your data, okay? That's a good one. And then I put some timing in there so we can see how much time it ran. And this bottom one's actually gonna be very, let me see if I can go farther. I cannot, but can you see it there? I know some of the computers kinda, okay, in the middle, this save RDS one. Actually, I can. There we go. Okay, so the save RDS one, and this is gonna be pretty important for those who keep on doing R regularly. You can save results as an RDS file, and then that allows you to import it as a variable to the existing file. So this puts all results in a file, and then I can put that file straight into R, and it becomes a variable immediately. Okay, and I'll actually show you how to do it right after this, but RDS is super helpful if you're running multiple R scripts and you need to combine results at the end. RDS will let you do it. Okay, so, okay, and important command at the end, subcluster. I'm done. My parallel section is over. So that means if the parallel section is over, there has to be a start, right? So here I'm defining the starting the cluster. So everything before this was done serially. It was done in sequence. I do this, I do this, I do this, I do this, and then only this section.
Somebody opened the door.
Only this section is parallel, okay? That's important to know when you're writing your scripts. Your entire script's not parallel. Just the section that I defined as parallel is, okay? And that's pretty, so for example, the thing that made our models, right? There's a for loop in there. I could try to make that parallel. In our case, pretty small, all models. So I wouldn't try to, right? So we can select what things to parallelize and what things to not. Okay, and that's important, also important to know. So this is the file that we're working on today. So you close it without saving because I don't want the errors to pop up, right? So now we have our R file, right? So now what do we need to submit it? In our batch script, right? We don't have one yet, okay? So we're gonna go see how we submit one. Okay, so going back to the open on demand, I'm actually gonna zoom in a little. Oh my God. And then, okay, we're good. It's messing with that. Okay, so we're gonna click on clusters, right? And you're gonna click on cluster shell access. Now this will give you, anybody familiar with the terminal before? Okay, oh, 4 out of 5. This is great. So terminals look like this, and they're the, oh, okay, Zoom is not working. So, right. There we go. Okay. Oh my. Oh. Give me a minute. Okay, I'm gonna keep it like this, unless Alex comes and saves my life.
Always,
Okay.
always plus,
Yeah.
control plus.
Okay. Thank you so much. Okay, so for those of you familiar with the terminal, right? Looks like this is the really cool thing that hackers use in movies. Seem very intelligent and they hack everything with a single click, okay? But in actuality, it takes some time to use. Okay, so the first one I'm gonna use actually a command called ls, which lists all your files. And you should see there. Actually, I'm gonna clear it so it appears higher on the screen. Yeah, so the ls command, right, lists all our files out. You should have the multi-node -r.r, which is the file we just talked about. And you should have a .sh file. That is my script file, okay? So to see what's in there, we're gonna use something called Vim, which is a text editor. So you're gonna type Vim. And then you're gonna multi-node.sh. Now, if you see me, the file appearing, this is me using the tab, okay? Tab auto completes our files. And enter, and you should see this, right? I know the colors are not visual friendly there, but everybody can read it kind of, and you have it on your computer, you see it there? The file? Okay, so. At the top, you'll see the same commands, right? Job name, thank you, Alex. I appreciate it. So the job name, the course, total nodes, the account, and the time. Then module load and then submit. In this case, we change to submit, so it is our actual file, right? Submitting multi-node -r. Okay, so it's the same batch script that we talked about earlier, right? We're just submitting our file, okay? And to exit, you're gonna click escape, then colon. Now we're escape, colon Q, right? You'll see at the bottom that colon and a Q appears. Click enter, and that should take you out. Why Q? Means quit, okay? On Vim, if you wanna write or change the file, it's colon WQ. W is write, Q is quit, okay? So that's how Vim does this. Any questions there with the batch file and the file? All good? Yes.
This is SBatch too. The hashtag SBatch making a bid file.
Yeah, so the hashtag SBatch, let me go back in. The hashtag SBatch file, the hashtag SBatch line is telling it that this is a Slurm instruction. Right? It's saying this is an instruction for what the job should be. Right? The bottom lines is like, these lines are gonna be run on the command line, like I type them and enter, it runs. The top ones is like, make sure that these are the job arguments. So that when the job runs, it runs for 30 minutes, it runs on this account, it runs with this name under this amount of cores, right? So these are the same instructions, actually, I can show you that. Okay, so these are the same instructions, right, that we saw on our studio when we wrote it, right? Slurm account, number of hours, amount of memory, number of cores, right? These are the same thing. SBatch, the hashtag SBatch lines are the same as defining them in here, right? It's the same, behind the scenes, that is what we're doing. We just put this up so it makes it way easier for you to submit stuff, right?
I don't know what the Slurm account, that's specifically for your end.
Yeah, that's just letting us know where your job goes. That's it. Yeah, so actually, I should have explained that at the beginning. The Slurm accounts, as I said, like basically we have a general, so the one that says here, general access, that's the one open for all of campus, right? Any student, faculty, staff can submit a job in the general access account, right? And it goes into a list, it goes into a queue, like what happened earlier. We have to wait until, okay? So that's what we mean with the Slurm account. We also call it a queue or partition. It's all means the same. Okay. Okay. So, does that make sense for the SBatch lines?
Yeah.
Yeah. All right. Now, let me get out of here again. Okay, so now we're actually gonna submit our job there. And we do that by using SBatch. And we write the one, right? And once we click enter, it should say, I have submitted your job. Now, we remember that the job is the code with the program. In our case, it's all together, but if you were making a really complex program, you could submit a job that has a big Excel sheet or anything like that, and also the code itself. Okay, so once the job is submitted, It'll take a while. You don't have to follow me on this one, just to show you where jobs land. You'll see them under active jobs on there, right? You'll see that mine has two. It has the one that's running, this one that says RStudio is the RStudio one that I'm running right now, right? And this one that says multi-node. Now, that was pretty quick because it says it's already been completed, which is good, right? It tells you where, how many CPU, how many cores you use, how many nodes you use, how much time was used. In this case, super short time, right? But in case you're able troubleshooting your own stuff, it's nice to know. Okay, so let's go back. Hope you didn't follow me there. And now if you do LS on your account, you should see a couple more files this time around, right? You should see R out. You should see Slurm out, and you should see your regression results, right? And that should be the actual regression results from your program. Yeah. Now we can check. If I actually don't type this one up because I don't know if it's gonna work or not. Okay, so this is the output file for the R. This is what actually ran. So you can see here, ignore the warnings as we do all the time and why we run into trouble. This one tells us what it was running. Right? It says it was running on computer number 3558, computer number 35512. And that means nothing to you guys. It shouldn't. It means something to us because we know what computer it is on physically on our supercomputer. And for us, troubleshooting wise makes sense. But for you guys, the important thing is that if the number at the end was different, is that it was running on two different nodes. And that's cool. We did it. We're running on two different computers, 2 cores on each one, right? It gives you information of what each of those is. And it tells you the amount of time. So here you can see that. See, user time, elapsed time. You see that? 052. That's how much time it actually took. It was, again, slower, right? Because it took way more time to coordinate across 2 nodes, send the information back and forth, and run. Okay? It wasn't that much more time, right? And then at the end, this process time, how much did it take that whole, bless you, how much did it take that whole job to run? So not only the parallel part, the whole thing, from the minute you open the file, to the minute you close. Okay, so that doesn't really matter for our parallel timing. This is the important one. We see that the elapsed one is higher because of memory constraints and having to arrange anything, but the user one, super, which is good, which means we're running our models in parallel. Okay, now let's look at everybody run it. Actually ran the thing, okay, and the ULS, and you saw the regression results was in there. Yeah. Okay, so the last part of this is to actually import our results back. So going back into your R, right? Now you're gonna be able to file and open file. And in your files, you should have regression results RDS. Open that one, it'll give you this box that says load regression results into an R object. You click yes, please load them up. And when they're there, you can see that the list appears as a normal variable, right? Your results are nice and tidy, and I can use them again in R. I don't need to import it as a separate file or as a separate Excel sheet, okay? Or as a separate, object that I need to turn again into a file. Right, so you'll see that each of these is the summary for that specific model, right? And we can actually open all of these and see them. So these are all the summary results for each of these models, right? The formula itself, the coefficients, all the results there, okay? Does that make sense there? Was everybody able to import it, the regression results in there?
Mine is still cute.
Your job is so cute. Should I take a look there if you can?
Probably.
Everybody there good? We would run it? Were you able to import it in the result? Good. Okay.
通知到partition 区 backfill 区。
Any questions online, Alex?
Could you show me again how to load and open the regression results?
Yeah, definitely. So you're gonna go up to the file and open file up there. And you should see regression results RDS there. If you do not see it, your job has still not.
I saw it.
All good? Okay.
Yeah, but as long after I click the load RDS, it
Mhm.
just show, yeah, it.
Oh, yeah, it appears on this side, on the environment side.
Oh, it's in the
You
environment.
Scroll down until you find it there. It should be on the data. Top ones.
Oh, that's right.
All good there? Found it? With the job? Okay, so. And that last example was what type of computing? Was it shared memory or distributed? Okay, cool. So we covered both of the big ones, distributed computing, shared memory computing, right? And we did an example for each one. Now, I'm not gonna lie to you, that was a really small example, right? In the real world of parallel computing, in really big applications, you will run into way many issues that we cannot cover today. But just giving you, I hope that this gave you an idea of what you can use. The easiest ones and the ones I would really suggest for you to really keep on trying is that MCL apply one, right? Super easy to run a function across cores quickly, okay, even in your own computer. For the distributed computing ones, getting really familiar with the one I used to write the other one was called, it wasn't parallel R, it was trying to remember, or just to give you an idea, yeah, it was still the parallel library, right? But it is the additional function. So the function, if you are interested in finding more information about it, right? I would try finding more information about how to make clusters. That's how R calls it. In this case, we made a PSOC cluster, but the terminology is not important. As long as you look up documentation of making clusters in R, it will teach you how to export clusters, how to read data back in, how to send messages between one and the other, right? And this is more heavy duty stuff, right? So these are kind of the resources that I can send you to for doing this, okay? And yeah, and that concludes today. If you have any questions, please let us know. We'll stick around for a while. If you have any ideas or stuff that you're working with, we can talk with you. Yeah, and that was all for today. Thank you so much for coming. Hope to see you again in our next one.